Hello, this is the second lecture on Fourier series. I've done the Fourier series of y is equal to x in the interval minus pi to pi. This time I'm going to do the Fourier series of y is equal to x squared, and let's not put pi's this time. It'll make things a little bit easier if we put the pi's, but yeah, let's put it from -1 to 1. And I have to stress, it doesn't have to be symmetrical between -1 and 1. It could be any interval, but normally we'll have it in a kind of symmetrical interval because it makes life easier. Okay, so I'm going to write the Fourier series theorem down, or the Fourier theorem rather down, which says basically if f of x is continuous, so we have for reference, they're continuous, piecewise continuous, so okay, let me just write it so to be perfectly correct. Piecewise continuous, hope I spelled it all correctly as well, in the interval, let's say, -L to L. You can often, in the most general form, the interval should be alpha, comma, alpha plus 2 lambda, not lambda, 2L. So basically it could be anything, and this L represents the half period basically. But normally we pick symmetrical, that's what I was saying earlier on. And then the following thing is true. Okay, so f of x can be expressed in terms of sines and cosines by the following: a naught over 2, and we have the sigma. Let's use n's for this one. N is equal to 1 to infinity, and we have an cos n pi x over L plus bn sine n pi x over L. Okay, where of course these coefficients a, n from n is equal to 1, including the 0, so I'm going to put them all together. An is 1 over L, and we go minus L to L, and we got f of x cos n pi x over L dx, and the bn's have a similar structure. The only thing that differs, we have sines instead. So the a's are the causes and the b's are the sines. They always are. So what is that? You can think of it like in the Maclaurin expansion. No relationship in the maths behind it, but the same way we can expand a function in terms of polynomials, we can expand a function in a given interval in terms of sines and cosines. Okay, so in this particular case, let's go into work. So I'm going to leave that up here, so for reference, and I hope I have enough room here to do all my workings. Okay, so in this particular case, we have f of x is equal to x squared. So I'm going to do the bn's first, because the bn's, of course, they're going to be 0. Why is that? Well, first of all, the interval is from -1 to 1. So your L in this particular case is in fact 1. Okay, so that's -1 to 1. So that's 1 over 1. Bn is 1 over 1. And we have the integral from -1 to 1. And we got x squared. That's the f of x sine dx, and of course if n is an integer, then of course this is odd, this is even. Overall your function, the integrand, will be an odd function in a symmetrical domain. Of course this will give you 0. So there's no bn's in the expansion of that. There'll be just causes basically. So let's throw this away and just say in this particular case, you can put the justification. That's what will always happen, of course, but I've just written it down so we can all see it. bn's are 0. So now the an's. Let's work out the a0 first of all. The a0 is 1 over 1, the 1 over L. The integral from -1 to 1. Your f of x is, of course, x squared. The cos, remember we're doing a 0, so n is 0, so it's the cos of 0, which is 1, of course. So that's the integral simply, minus 1 to 1 x squared dx, which is an even function, so we can write it as two lots from 0 to 1 x squared dx, which of course will integrate to 2/3 x cubed between 0 and 1, and the answer is 2/3. Okay, so, and a naught, so I'm writing the results up here. A naught is actually 2/3. So we're going to get now the general ANs. So this is going to be a little bit messy, but because this will have two integration by parts unknowingly. So let's look at the AN. For n 1, 2, 3, 4, 5, the 0 we've done it separately here. So that's going to be 1 over 1. I'm not going to write it. Integral from minus 1 to 1 x squared cos of n pi x over 1. First of all, make life easier immediately. Even function, overall even, two lots from minus 1 to 1. And probably because I might make a mistake in my integration by parts, I might write this inside and treat it as being part of the 2x squared. So, sorry, there should be two lots from 0 to 1, 2x squared and pi x dx. So we have to do this integral. Integration by parts, very annoying. So we have 2x squared cos of n pi x, 4x, and this is going to be 1 over n pi sine of n pi x. So for this particular question, we continue with the bits. Don't know if I have enough room to actually fit it in here, so I'll try to squeeze it. So we got that product, 2x squared over n pi sine of n pi x has been integrated 0 to 1 minus the integral of this diagonal, and this diagonal will be let's put the 1 of, it doesn't matter now, I'm going to put it inside so to save space. Normally I would have written this 1 over n pi on the outside, so it's going to be 4x over n pi sine n pi x dx. Managed to squeeze it, 0 to 1. Okay, I claim this is 0. When x is equal to 1, the sine of n pi, where n is an integer, is 0. When we go to the 0 limit, it just dies from here straight away. So what we've got in there, just doing a bit of a tidy, minus 4 over n pi. I pull the 4 over n pi outside the interval with a minus, and we go 0 to 1 x sine, I'm missing an n in there, I do apologize, it says sine pi x, should be sine n pi x. I'll leave it, sine of n pi x dx. Okay, another integration by parts. So x sine of n pi x, 1, and this is now a minus 1 over n pi, and a cos of n pi x. So that's going to be minus 4 over n pi, big curly bracket, product of this column, so it's going to give me a minus x over n pi cos n pi x. So make sure you know how to do your integration by parts, whichever way you use. So that's the product of that, and then it's minus the integral, and of course this is to be evaluated between 0 and 1, minus the integral of the product of this diagonal, and of course that has a minus already, so I'm going to switch that into a plus, 1 over n pi cos of n pi x dx. Okay, first of all, does that die? It doesn't quite die like the previous one. So because I've got this floating bit, I'll probably do a bit of a tidy first of all. So I'm gonna have this first of all is going to, I'm gonna take this minus outside this bracket here, make it to a plus, minus times a minus, and I'm gonna have a 4x, no 4x, that cannot, needs to be evaluated, I beg your pardon, 4 over n squared pi squared, this is that times that, and inside there I'm gonna have x cos n pi x between 0 and 1, just double checking, minus minus gives me plus 4 n pi blah, 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 x cos n pi x, and now I have a minus, and I have a, as in front of the integral, a 4 n squared pi squared, and I still have to integrate the cos of n pi x dx. I don't think that will be 0 on the next integration. So if we start evaluating this quantity, 4 over n squared pi squared, when we're putting 1 in there, we're going to get the cos of n pi, and when we put 0, this is dead because of the x. And this is going to be minus 4 over n squared pi squared times 1 over n pi, integrating the cos, sine of n pi x, and of course at 1 we have the sine of n pi, so that's an integer value, it'll be 0, and at 0 it'll be 0, so this bit here in fact is 0. And of course the cos of n pi, I have mentioned it in the past, the cos of n pi can be written compactly as minus 1 to the n. You can try different values of n and see that this is actually correct. So it's actually, this occurs in many places in mathematics, and it's easier to, it's a fact that it's easy verifiable and it's easier to write. So we can actually say there, this is in fact 4, actually I'll write it up here, the b, sorry, that's the ans. Ans are 4 equal to 4 minus 1 to the power of n over n squared pi squared. So let's clear the board and see what we actually have done. So at the moment, what we've done so far is we have computed ans and bns, and we have them up here. So I'm going to make sure that I don't rub these things by mistake. And then we have done all this work, and I certainly don't think I will be remembering this. Okay, so just do it patiently. And what have we got so far? We found that f of x, which of course is our x squared, in the interval minus 1 to 1, can be written as a naught over 2. What was the a naught? It was 2/3, so in this particular case, it will be just simply a third, because it has to be divided by 2. We found that the bn's are 0, there's no sign bits in there, plus the sum from n is equal to 1 to infinity. The an's turned out to be 4 minus 1 to the power of n, n squared over pi squared, and then it's going to be, of course, the cos. Remember, the L is 1, so it's the cos of n pi x. And we can pull some bits on the outside. So for something like this, we can pull perhaps, not that you have to, plus 4 outside the sigma. At the end, no, of course, because it's n in there, so pi squared. I think that's about it, isn't it? And then we can write the sigma a little bit with a little bit less mess inside it. So it's going to be, of course, minus 1 to the power of n divided by n squared cos of n pi x. So that's the argument of the sigma. And what, because this is like written in compact form. Of course, you can write a few terms of this. I'm going to write a few terms when I rub them off afterwards. So we got a third plus over 4 over pi squared. And if we put n is equal to 1, maybe we should have written it as the other, put an n plus 1, put a minus on the other side to make it easier. N is equal to 1 will return me negative, unfortunately. Minus, we're putting now for the x is equal to 1, so it's cosine pi, so we're going to have a minus 1. Sorry, I'm writing stupid things. Cosine pi, I'm putting n is equal to 1, not x, sorry. N is equal to 1, so that's cos of pi x oops, I've taken care of that, sorry. I'm getting absent mind. That's the minus 1 to the 1, that's a minus. And we got a cos of pi x over, I can put the 1 squared so we can follow the pattern. It's going to go plus, because we're putting 2 there, so I'll square out. And we're going to have, of course, a 2 squared. And it's going to be a cos of 2 pi x. And it's going to go minus again. It's going to be, of course, a 3 squared. And it's going to be a cos of 3 pi x plus dot 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 forever. So we're expanding this in terms of causes. And what it will look like on a graph, unfortunately, I cannot show you. My computer does it. I use a very old-fashioned system, but it's, in my opinion, one of the best. I'm still going. I'm using Derive 6, and you can do Fourier series very nicely. If you can imagine what we have in here, we have the graph of y is equal to x squared, and we have it from 1 to minus 1, so that's up to 1 here as well, and minus 1 in there. Okay, what happens if we plot this bit here and we take enough terms? If we take enough terms to infinity, it will match perfectly. But if we take, let's say, the first 10 or 20 terms, it's going to look something like that. It's going to be something like a wavy quadratic up to 1, and then it will suddenly repeat itself. So that's the 1. It will touch a 2, 3, and then, of course, the more terms you take, the less of this effect you will have, and it'll be straighter and straighter. It's really important to actually see it at some point. I mean, it's Mr. Fourier back in the early 1800s. I mean, it must have been amazing to think of such a perverse thing without technology, without anything, and so on, of course. So it will look something like this. Okay, so it will be, this is, of course, the minus 1 to 1, and we're getting a periodic repeat like this. And this is what Fourier series is all about. Okay, this particular question that I'm doing, it has a second part. And the second part, the first part was just to find the Fourier series of this. The second part was to find the exact value of this series, which is 1 minus a quarter plus a ninth minus 1 over 16 plus 1 over 25 minus 1 over 36 plus dot dot dot. So it's clearly related to what we have done so far. So let's see what we need to be looking at here. We need to be looking at x squared, and we need to be looking at this bit here. So x squared is equal to that. So we need to put a suitable value for the x. So what's a suitable value for the x for this one? A suitable value for the x will be nice numbers like a 0, a pi over 2, things like that. Here we don't want a pi over 2, obviously, or something, because we already got pi's. So let x is equal to 0. Let's see what happens. So we're getting 0 squared is equal to a third plus 4 over pi squared. And then if we put x is equal to 0, the cos of 0 is 1. So this becomes a 1 times the sigma from n is equal to 1 to infinity. And I think that does it, doesn't it? Because I'm getting alternating terms and I have squares. So what I'm going to do on this line, I hope it's visible. I want to go on black pen, which is a little bit thinner. I'm going to write this now as, I leave the third. Take that on the left. And we have minus 1 to the power of n over n squared. And we have 1/3 on the right, but I need to divide this by this coefficient I got at the front, which is, of course, 4 over pi squared. So it's going to be a pi squared over 4. And then I'm going to do one more thing. I'm going to take this minus and put it inside. So it's going to be to the n plus 1. And of course, this is going to be pi squared over 12. Now, I claim this is that. And we can check it. When n is equal to 1, that's going to go positive because it's going to be squared over 1 squared, which of course we don't write. When n is equal to 2, that's going to go negative. And of course, we're going to have 2 squared, which is a 4. When n is equal to 3, that's going to go back to positive, and that's going to be 3 squared, which is 9, and so on. So the answer, this particular infinite series, can be summed very easily using Fourier series, and the answer is, of course, pi squared over 12. Hope you apologize for my cough. I'm not very well. I don't know how long I'll be able to still be providing videos and resources. I got a little bit desperate lately, and I'm trying to do as much as I can, which doesn't help. But for the time being, I hope you find this particular useful, this particular video. And this is the second of the examples in Fourier series. I'll be seeing you real soon. Bye for now.